Hi, important derivation of some equations regarding feedback amplifiers. One of the important topologies, voltage series feedback amplifier, making use of a BJT. BJT. The question is, remember, we have three configurations of a transistor, and which configuration falls under the classification of voltage series feedback amplifier? It's common collector configuration. Alright, it's common collector configuration, which is also known by the name emitter follower. So remember this one, you have that exam point of view, very much important. And where to start from the circuit diagram, guys, the transistor. All right, we have the transistor. This is the base, and what components do we have around this one? Here we have RC and plus VCC to provide the necessary biasing, and we have RE grounded, across which the output voltage is collected. All right, so here we collect the output voltage with respect to ground. So, and here is the place where we provide with the source voltage Vs the signal to be amplified. All right, we have the internal resistance of the source Rs. All right, so what voltage do we have here? We have V in. All right, so we have V in. So this is a closed loop. All right, this is a closed loop. So how to write down this one? Nothing in between. All right, so we start from the ground, we go coming back to the ground. So this will be a closed loop. So how to write the expression for this one? Vs will be equal to V in plus V naught. All right, so V naught, its output voltage, okay, that is the same amount is added in the input, it's a feedback. This voltage, the same voltage, is included in the input, included in the sense added in the input, is given back to the input. So it's V naught will be Vf in this case, especially in the common collector configuration. Whatever output voltage, whatever voltage taken as output, the same is given back to the input without any reduction or anything else like that. So this won't be V naught, it will be Vf. All right, so from which we have V in, the voltage which is fed to the transistor is equal to Vs minus Vf. So this is the feedback voltage. So with the increase in the feedback voltage, there is a reduction in V in, and so all these comes under negative feedback. I repeat, with this one, with the increase in the feedback voltage, there is a reduction in Vin. I mean, Vin will be approaching more and more negative. That the transistor is reverse biased. All right, so see 10 volts, Vs is 10 volts, and 6 volts, 7 volts, 8 volts. What is happening with the Vin? There's a reduction, isn't it? So with the increase in Vin, there is a reduction. I mean, with the increase in the feedback voltage, there is a reduction in the input voltage given to the input voltage which is reaching the transistor, and so this configuration is known as a negative feedback, not the positive feedback, and that is employed in amplification. All right, so this is the one, and a little information to be known from the block text reduction again. So the main amplifier with the gain A, and the feedback amplifier with the beta. So we have that RL and V naught, across which we collect the output voltage, and this is what voltage sampling, isn't it? And given back to in series some voltage, like voltage is given in series, not current. All right, so we have Vf over here, Vf which is equal to beta V naught is given back to the input, in the sense V in appears over here, that Vf comes over here, and that Vs comes over here. All right, all are in series, all the three drops are in series, and so series voltage, it's in the feedback voltage is in series with something. What something? The source voltage and the input voltage to the transistor. All right, and from here Vin is equal to Vs minus Vf, isn't it? And remember, we have two ratios. We have AV, voltage gain without feedback, and AVF with the feedback. So AV is simply V naught by V in, and if you obtain the ratio between complete output voltage by the source voltage Vs, that is this one. Please remember these points. All right, so here evaluating for AVF, with the feedback, voltage gain with the feedback, it's V naught by Vs. All right, so what do we have? V naught is equal to, from here, V naught is equal to A times AV times Vn. This Vn is nothing but this Vn here, this Vn, and V naught AV as it is. Vn is this one. Vn is this one. In the sense, Vs minus AV Vf. Vn, this Vn is equal to Vs minus Vf is plugged in over here. All right. So there is small another modification over here. AV Vs also as it is. AV also. Vf is this one, beta V naught. So AV beta V naught. It's negative. This pulling this towards this side, that will be positive. So V naught plus AV beta V naught, which is equal to AV Vs. V naught as common, 1 plus AV beta, which is equal to AV Vs. So that ratio V naught by Vs, that will be equal to AV by 1 plus AV into beta. What? Now this is AVF. So AVF. So if you have a question, draw the circuit diagram of a voltage series feedback amplifier using BJT and derive expressions. Yeah, what questions will be asked? You will be asked to derive the expressions for voltage gain with the feedback AVF, and input resistance with the feedback, input resistance with the feedback RNF, and output resistance with the feedback R0F. All right. So it's simply AVF. It's now AV by 1 plus AV into beta. Just now we have done this. All right, and let me provide you the link. Previous to this video, I have derived expression for RNF. It's a Rn into 1 plus AV into beta, right? So R0 by 1 plus AV into beta. We have done this. We have that when we have that proof. So here, as far as this discussion is concerned regarding voltage series feedback amplifier and deriving expression for all these three, let's straight away obtaining the hybrid model of this one, making use of the approximate hybrid model of this one, and evaluating AV and beta, plugging in, that will give us all these values. The simple method to evaluate that expressions, very important one, voltage series feedback amplifier, repeatedly asked when compared to other topologies. We have 4 topologies, isn't it? So here, and from here itself we can evaluate beta. So guys, this is V naught, and what is beta? Yeah, what is beta? From the general knowledge of block diagram reduction in the feedback, it's a beta is equal to Vf by V naught from the block diagrams, that block diagram representation of a feedback amplifiers. And now if this, like these two are equal, whatever V naught is taken, whatever the output voltage, the same, the full quantity of output voltage is included in the input. So these two are equal, in the sense when these two are equal, the ratio will be equal to 1, in the sense beta equal to 1 for this configuration. That's made, that is plugged over here, here and here. All right, so now if we could evaluate AV, it would be simpler for us to evaluate this one. And once we have AV, we have beta. It's a unity. Why? Because V naught, the same amount is given back to input. Vf is equal to V naught, so that's beta. So making evaluating AV and beta will make us easier to evaluate all these three expressions. All right, now what is AV? Generally AV is V naught by V in, not AVF. Okay, we didn't arrive to AVF. Evaluating AV, then plugging in over here beta, we have AV there, so that we'll have to do this. So not with this one. Remember, beta value is unity for this configuration, not the transistor but the approximate hybrid model. How that approximate hybrid model looks like, and input is given to the base here. This is the base. All right, so base, in the base terminal, what do we have in the approximate hybrid model? It's a HIE. All right, and collector over here, collector with the IC, and we have a current generator in the collector terminal. Remember that one for the approximate hybrid, HFEIB, and this is the emitter. All right, This is the emitter. Now what about this? This representation is regarding the transistor. We are done with, with the transistor. We have represented the transistor in its approximate hybrid model. Where does this come? Here we have to the base, isn't it? To the base. We have that voltage. We have that voltage which is to be amplified, VF, VS source voltage, with the series resistance, internal resistance of this one, RS. All right, we are done with this. Where we have this one? In the emitter, isn't it? Here we have the emitter and we have RE grounded. It's grounded, across which we are collecting the output voltage V naught, and the same, the same voltage is given back to the input, so VF. All right, so we are done with this one. Right, transistor also exists. And what is this terminal? It's a collector and RC. Collector over here, so RC we have here, and that's grounded. RC, this is the complete arrangement. All right, so this is the transformation which we have to make use of to do the simplification. Now here, this is V naught. Here we have the V naught over here. Whatever current flows through this one, that into RE, V naught will be equal to what? V naught. RE, we have the resistance. What current flows through is this side. See, IB will be pointing towards this side, IC also. So IB will be in terms of milliamperes. This will be in amperes and this will be in milliamperes. In the sense, we have that, isn't it? IE approximately equal to IC. So what is IC? IC is this, the same current. IC, the same, that it's in the same loop, isn't it? So the same current, and that current will be flowing towards this side. Okay, even this current flows towards this side to the ground, but neglected, very little amount, which has no much significance. All right, so this resistance RE and into IC, okay, but IC is equal to HFE IB, the current generator. HFE IB for V naught. Now what is Vn? What do we have? Vn, actually, okay, leave it out. Vn is the input current IB multiplied with the input resistance HIE. All right, but this also adds some significance, so plus it's in series, so RS. That's for Vn. Now the ratio AV, which is equal to V naught by Vn, which is equal to, what's V naught here? V naught by Vn, which is equal to AV. What is it? By Vn is this one, IB into HIE plus RS. All right, AV. So what gets cancelled over here? This is IB gets cancelled. So HFE RE upon HIE plus RS. Guys, this is only for AV. All right, this is for AV, only for this ratio is only for AV. And to evaluate AVF, what do we need? We need that expression here, coming back to that one. AVF, voltage gain with the feedback, AV upon 1 plus AV into beta. Beta was found out to be unity. Beta is unity in this case. Why? Because the same V naught and VF are equal. It's not a proportion, it's not a half value or anything like that. So AV upon 1 plus AV into beta. So AV is this much. So over here, all right. So AV, it's a HFE RE by HIE plus RS upon 1 plus AV. Beta is anyway unity, so this comes down as it is. So HFE RE by HIE plus RS by 1. Simplifying this one, AVF will be equal to, so here this gets cross multiplied, isn't it? So in that case, HFE RS by, sorry, RE upon HIE plus RS, and this one, this appears as it is. In the LCM will be HIE plus RS. This appears over here, HIE plus RS plus, isn't it? Plus HFE RE. Right, simplifying this one, don't get confused, is small simplification. So HIE RS gets cancelled, and AV Vf will be equal to HFE RE by HIE plus RS plus HFE RE. All right. So guys, when compared to this one, this is HIE will be in terms of ohms, 100 ohms approximately. RS also will be very less. This will be in terms of kilos. So this is so small, this is so small. All right, so even if it's included, this will be approximately equal to 1. The voltage gain for a common collector configuration, a transistor in common collector configuration has unity voltage gain. This is the proof. All right, we can prove that in numericals when we have these values HFE RE, HFE, this one, this is in the order of, this will be in kilos and this will be in the order of ohms, so approximately 0.99 like that, which is approximately equal to unity. You can say this or give this statements explaining all this, that will be more impressive. All right, now this is for ABF. Now evaluating the second one. What is the second one? R in F, right? So what will be 1 plus AV beta? This is, I guess, completely no. What is 1 plus AV beta? We don't need this anymore. All right, why? Because now we need for R. What is R naught? R naught is the output resistance, and here the load resistance itself, like where is the load resistance? Output generally what is like output voltage collected across what? Load resistance, output resistance, and that R naught will be equal to RE in this case, which will be R naught. All right, that has to be plugged in over here, and before that it will be more convenient to evaluate. We have this one. All right, 1 plus AV beta, 1 plus AV into beta. So this is, let's say it's a D, standard textbooks authors, they follow this one D. Okay, like AVF will be equal to AV by D, like that. So 1 plus AV is, where did we have AV? This one. Beta is anyway unity, so this one, it's a HFE RE by HIE plus RS. So this one, simplifying this one, what do we have? It's a HIE plus RS, HIE plus RS plus HFE RE. All right, this is for the factor D. Right, now RNF, R input resistance with the feedback, it's a Rn into 1 plus AV into beta. All right, now what is Rin in general? Rin, like input resistance of the transistor. So what do we have? Vin is the input voltage and Ib is the input current. So Vin by Ib will be equal to Rin, which is equal to what? Vin by Ib, previously we had this one, like Vin by, like what it was, Vin is actually Ib into HIE, isn't it? The input resistance plus RS comes into the picture. That also has some little influence. So which is very much similar to Ib into Rn. So Rn, which is Vin by Ib in general, so Rn will be equal to that itself, right? So what do we have? Rn, we have a HIE plus RS into 1 plus AV into beta. All right, so beta is anyway unity. All right, beta is anyway unity and AV is this one. I mean, guys, we have that 1 plus AV beta, so to plug in directly, we have made use of this one. So it's a HIE, it's a 1 plus AV beta, isn't it? This is the result for 1 plus AV beta. Why to compute that again? HIE plus RS plus HFE into RE upon HIE plus RS. All right, so this gets cancelled, this gets cancelled, and this is the expression for input resistance with the feedback. This will be left over. What will be left over? This gets cancelled over here and over here. This is the expression for the input resistance with the feedback of this configuration. And usually they say, what the expert says is, what the practical usage says is, this combination HI plus RS is very much less when compared to this one. Okay, you may leave it over here itself, saying that this is the expression for input resistance with the feedback. Now coming to the third one, R naught F, which is R naught by D, right, which is equal to RE. All right, RE, R naught is RE itself, D is this one, D is which one, this one, which flips up. So what do we have? HIE into HIE plus RS by D, isn't it? By 1 plus AB beta, that flips up. So we have HIE plus RS plus HFE RE. So let me erase this away so that you can have a clear picture of that one. So we will be left with this one. Any simplification, guys? What do we have? Yeah, that's it, right? Expression for output resistance with the feedback. This will be reduced numerically. If we solve any problem with all these values, we can find out this is very higher value, and this is, there is a reduction in the resistance, right? So these are the expressions AVF, RIF and R naught F. So thanks for watching.